Chapter 4 is proof techniques, and again, I'm going under the assumption that you do have some experience with different types of proofs. Hopefully, these examples will help you in your studies. On problem number 1, it says prove if A is a subset of B and B is a subset of C, then A is a subset of C. We could do Venn diagrams to illustrate this. Let's look at A as a subset of B. If A is a subset of B, then that means that all elements inside of A, by default, these elements are also inside set B. And if B is a subset of C, then that means all elements inside B are in set C. And that's essentially what we're going to do in the formal proof. Let's let X be an element of A. Change colors here. So let X be an element of A, and since A is a subset of B, then X is contained in B as well, which we can see. So if we draw a ring here to illustrate the boundary for B, we can see that X is contained inside set B. So what have we done so far? We have established that X is an element of A, therefore X is an element of B, because A is a subset of B. And since B is a subset of C, then all elements inside of B are also in C. Therefore, A is a subset of C. Notice any element, in this case we chose arbitrary X. X is contained, right, in this outer ring here. Notice that X is inside of C. So any element in A is also in C. Okay, number 2. Prove if the sum of the digits in a 3-digit integer is divisible by 3, then the integer is divisible by 3. Okay. I decided to let the 3-digit integer be represented by, let me get my pen here. I decided to represent the 3-digit integer with JKL. And if we were to expand this, JKL is simply 100 times J plus 10 times K plus 1, plus L. And we decided to, I decided to set that equal to N. So N is equal to JKL. And again, all we did was we just expanded it to get this form here. For example, if JKL happened to be 360, that would be equivalent to saying 100 times 3 plus 10 times 6 plus 0. And of course, JKL and N are all inside of the set of integers, Z. So let's go back to what the problem says. It says, if the sum of the digits in a 3-digit integer is divisible by 3. Let's work with that for a second. The sum of the digits would look like this: J plus K plus L. And if J plus K plus L is divisible by 3, that means that J plus K plus L must be some multiple of 3, where M is an integer. The next step for me was to simply solve for J in terms of M, K, and L. So J is equal to 3M minus K minus L. And that came from the expansion up here. At this point, I went back to the original expansion on the top line of the proof. And in place of J, I substituted in 3M minus K minus L. And if I distribute the 100 across, that gave me 300M minus 90K minus 99L. How did I get that? Well, 100 times 3m is 300m. And then 100 times negative 1k would be negative 100k, but I must add the 10k here, which would give me the negative 90k. And then the same logic with L. Notice that my coefficient values are 300, 90, negative 90, and negative 99. I can factor a 3 out, which clearly shows that n is a multiple of 3, and therefore n is divisible by 3. Problem number 3. Prove the product of two rational numbers is rational. A rational number may be expressed as a fraction. Most textbooks tend to use P over Q, where P and Q are integers, and Q, of course, is not 0. So a rational number may be expressed as a fraction, where the numerator and the denominator are integers, and the denominator, of course, is not 0. And we're trying to prove that the product of two rational numbers is also rational. Let's let our rational numbers be x and y. And since they are rational, they can be expressed as fractions. So let's let x equal a over b and y equals c over d. Of course, b and d cannot be 0. What are we trying to prove? We're trying to prove that the product of x and y would yield another rational number. If we multiply x times y by substitution over here, that's going to give me AC over BD. Well, what happens if you multiply two integers together? You just get another integer. So I could say that A times C, for example, is equal to Q. And then B times D could be for, let's say, R. In other words, AC over BD is equal to Q over R, where Q and R are integers. And if B and D are not 0, R cannot be 0. So we have just shown that if you multiply two rational numbers, that product is a rational number. Number 4, prove the following. If 3n plus 2 is even, then n is even. As I stated here in the notes, my initial plan was to set 3n plus 2 equal to 2m, which would show that 3n plus 2 is even, but then the arithmetic got a little saucy for this lesson, so I decided to go back and try a different approach. And I wanted to leave that in here just to show that proofwriting it's not always simple. Sometimes you do start one way and you realize, you know, this was probably not the best approach, and then you try another avenue. And that's what I did here. So I left that in here just so you know that even math professors at times get frustrated with their proofwriting attempts, and they have to start over, which is what I did here. So what did I do? If you recall from high school geometry, this type of statement here is called a conditional. It's an if P, then Q statement. And the conditional has a truth value. It's either true or false. Well, the contrapositive has the same truth value as its conditional. The contrapositive is not Q implies not P. So not Q implies not P. This is equivalent to if P, then Q. I decided to prove the contrapositive. The contrapositive would say if n is not even, then 3n plus 2 is not even. If 3n plus 2, if n is not even, then I can write it as 2 times k plus 1, which makes it odd. And let's see what happens by substitution. I'm going to let n be an odd number, 2k plus 1. Then I'm going to substitute the 2k plus 1, n for n, in 3n plus 2. Once I distribute, that gives me 6k plus 5. Little trick here. Instead of writing 6k plus 5, I broke it down to 6k plus 4 plus 1 so that I could factor a 2 out of the first two terms. That gives me 2 times the quantity 3k plus 2, and then I just tacked my plus 1 on the end. Now that I have written 3n plus 2 as 2 times an integer plus 1, then I know that 3n plus 2 is odd. I have shown that not q implies not p, which means p does imply q. Therefore, this statement in number 4 is valid or true. Number 5. Number 5 says to prove that the product of two odd numbers is odd. I'm going to let m and n be two odd numbers, 2k plus 1 and 2r plus 1 respectively, where m, k, n, and r are integers. Since they are both written as twice a number plus 1, then m and n are odd. If you multiply 2k plus 1 times 2r plus 1, if you were to FOIL that, you would get 4kr plus 2k plus 2r plus 1. That's just first, outside, inside, last. Notice that I can factor out a 2 from the first three terms, which gives me 2 times the quantity 2kr plus k plus 2, and then I just keep the plus 1. Now 2kr plus k plus 2 is just another integer, so I decided to call that p, which gives me 2p plus 1, and anytime you have twice a number plus 1, you have an odd number. So the product of two odd numbers produces another odd number. Number 6. How many people are required to guarantee that there are born on the same day? How many people are required to guarantee that 3 are born on the same day of the year? What I decided to do here was to illustrate the pigeonhole principle. If you're not familiar with the pigeonhole principle, you might want to Google it, check out some YouTube videos. But this is how I decided to explain it. Imagine that you had 366 mailboxes. We chose 366 because the problem says to consider a leap year. And let's label each mailbox 11, 12, all the way down to 1230 and 1231. Now, this is just a month-day illustration. In other words, the mailbox labeled 11 is for those who have January 1st birthdays. 12 would be the January 2nd birthdays. And finally, 1231 would be those who have December 31st birthdays. So we have 366 labeled mailboxes. And suppose you line up 366 people and you give them all a Sharpie and you say, everyone go to your mailbox that designates your birthday and mark it with an X. So all 366 take the Sharpies, they go to the respective mailboxes and they mark them with an X. Well, the most long and drawn out scenario would be if everyone happened to have a different birthday. That means that all of your mailboxes would have one X. So let's do the process again. Let's take another 366 people. Well, again, if they all have birthdays on different days, they will take their Sharpies, they will put the second X on every mailbox. and then they are done. Now every mailbox has been marked twice, which means that for each day of the year, 2 people had a birthday on that day. So let's get the next group of 366 people. Wouldn't it be true that the first person in the third round would have to put a third X on a mailbox, regardless of his birthday? For example, my birthday is March the 13th. So if I'm that first person in the third round, I would walk up and put an X on the 3-13 mailbox. So this is the concept that I decided to use. And that shows that the minimum number of people to guarantee that 3 people have the same birthday, you would have to have that first 2 groups of 366, and then you would take that first person in the third round. As soon as he or she marks that box, then we now have guaranteed that 3 people have the same birthday. So you would need 733 people in order to guarantee that. Number 7, prove by induction that n is less than 2 to the power of n for all positive integers n. So here's how a proof by induction works. The first thing you're going to do is you're going to start with your basis step. This is the classic first step. The problem says that n has to be positive. Therefore, I'm going to start with the smallest positive integer, 1. So let n equal 1. That gives us n is equal to 1, which has to be less than 2 to the power of 1. Therefore, the formula is true for the basis step. So we're off to a good start. I could continue to do this for n is equal to 2, n is equal to 3, and so on. But proof by induction allows us to take a shortcut. What we do, instead of going to 2 and then 3 and so on, we arbitrarily choose an integer n. And if this happens to work for an arbitrary integer, then it should work for all integers. This is called the hypothesis step. This is where we make an assumption. I'm going to assume that the formula does hold. In other words, I'm going to assume that n is less than 2 to the power of n. The third part, this is often the most tricky part, especially with inequalities. I have got to show that if my hypothesis step is true, I've got to show that that links me with a true statement when n is equal to k plus 1. In other words, based on our assumption, would n plus 1 be less than 2 to the power of n plus 1? Well, if n is less than 2n, if n is less than 2 to the power of n, let's add 1 to both sides. So I chose to add 1 to the left side, and I chose to add 1 to the right side. That gives me n plus 1 is less than 2 to the power of n plus 1. It gives us this part here. But 2 to the power of n plus 1 has to be less than 2 to the power of n plus 2 to the power of n. How do I know that? The smallest n can be is 1, which means this number here has to be at least 2. If this number is at least 2, 2 is bigger than 1. I know that the 2 to the power of n's are equal. But since 2 to the power of n is bigger than 1, this inequality here holds. In other words, 2 to the power of n plus 1 is less than 2 to the power of n plus 2 to the power of n. And then I did a little algebra trick here. I factored out 2 to the power of n, and that leaves me in parentheses 1 plus 1, because if I distribute 2 to the power of n, times 1 plus 2 to the power of n times 1, that's equivalent to 2 to the power of n plus 2 to the power of n. Why did I do that? I did that to show that I can rewrite that as 2 to the power of n times 2. And of course, when the bases are the same, right, you add the exponents, which gives me 2 to the power of n plus 1. That was a lot of work just to say this. If n is less than 2 to the power of n, then n plus 1 has to be less than 2 to the power of n plus 1. That completes the proof. If you review or study induction proofs, a lot of authors or professors, teachers will say that it's a lot like a domino effect. If you know that the first domino has fallen, and you know that the last domino has fallen, then you know that every domino in between has fallen. And essentially, that's what we did here. The first step, basically, is the first domino dropping. And then we have this step, which is the final domino falling. Since the first one fell and the last one fell, then everything in between had to fall as well. I prefer to explain this as a link of statements that we would use, let's say, in truth tables, which shows that if anything false happens to occur, then the entire statement is false. But that's for another lesson. So if you need more practice on proof by induction, I encourage you to investigate linear algebra. Maybe buy a linear algebra textbook, and you will have plenty of examples in that textbook for sure. Problem number 8. Prove that there exists a positive integer n such that the sum of all positive integers. Prove that there exists a positive integer n that is the sum of all positive integers less than n. Fortunately, this is an existence proof. An existence proof basically means I just have to find at least one example that makes the statement true. Because it says just show that it exists, that 1 does exist. Well, 3 is equal to 1 plus 2. In other words, there does exist a positive integer, in this case n, that is the sum of all positive integers less than n. And 1 and 2 are those positive integers less than 3. Number 9. Prove the sum of an irrational number and a rational number is an irrational number. In other words, an irrational number plus a rational number has to be irrational. This does seem logical when you consider the fact that an irrational number never ends and it has no discernible pattern. So imagine numbers of the most famous irrational number, pi, 3.1415, and so on. Pi does not terminate. Pi does not have a discernible pattern to it. So it seems rather intuitive or obvious that if you were to add a rational number to the irrational number, that it too would go on forever without a discernible pattern. But how do we express this in a meaningful way, a more concise way? I decided to do a proof by contradiction. When you do a proof by contradiction, you assume that the negation of the conclusion is true. If you make an assumption that it's true, but then later in the proof, if you see a contradiction, then you know who to blame, right? You know what to blame. You will blame your assumption, because everything else in the proof is backed up with either a definition or algebra or maybe a previous theorem. So if there is a flaw, if there is a contradiction, we will blame the assumption because the assumption is just what it is. It's not backed up by any evidence. I decided not to be fancy with this problem. This problem is straight from this textbook that's mentioned at the beginning of the algebra series in the narrative. So I decided to let z equal x plus y, where z is rational, because the negation of the conclusion would be that the sum is rational. That's the opposite of what I'm actually trying to prove. That's fine. That's the way proof by contradiction works. I'm going to let z be rational, and I'm going to claim that x is irrational and y is rational. So basically, I'm going to try to prove that if you take an irrational number, x, add it to a rational number, y, the sum is another rational number. If I solve for x, then that means that x is equal to z minus y. Since z and y are rational, they may be written as fractions. And if you subtract one fraction from another, you get another fraction. That means that x may be expressed as p over q. So x is rational, which contradicts my assumption. Everything else in the proof is valid. The algebra here is valid, but our assumption has caused a contradiction. Since we found a contradiction, then that means that the original statement is true. Our conclusion is that the sum of an irrational number and a rational number is irrational. And finally, number 10, prove by cases. Prove the following: 9n squared plus 3n minus 2 is even for all n in z. So we know that n has to be an integer. We know that if n is in the set of integers, then n must be either even or odd. And we're going to look at both cases. If I start off by letting n equal 2k, well, if a number is twice another number, then that number has to be even. In other words, n is even. If I substitute 2k for n throughout this equation here, or this statement here, that's going to give me 9 times 2k raised to the power of 2 plus 3 times 2k minus 2. A little algebra will show me that I can rewrite this as 2 times some quantity, that quantity being 18k to the power of 2 plus 3k minus 1. Anytime you can express a number as 2 times another number, anytime you can express an integer as 2 times another integer, then you have an even number. So that takes care of the even case. Let's take a look at the odd case. N is equal to 2k plus 1. If you can express a number as you can express an integer as twice an integer plus 1, then that given integer must be odd. And again, go back and substitute 2k plus 1 in for the original statement. That will eventually simplify down to 36k to the power of 2 plus 42k plus 10. And of course, since 36 and 42 and 10 are all even numbers, I can factor a 2 out. And since I can factor a 2 out of this expression, that means that I have an even number. So we have shown that using the even case and the odd case, that 9n squared plus 3n minus 2 has to be even.